All right, let's go ahead and take a look at some of these function transformations. We're just going to go over a couple of examples. And the first thing we're going to do is just graph the parent function. F of x equals, and we'll use the square root of x as our example. Okay, so how do we graph this? Well, if we're given a function and we don't know exactly what it looks like, we can make a table of values and just plug in a bunch of numbers that would, so we get some points. All right. So let's go ahead and do that. And we'll pick these numbers, specifically so that they work out to nice numbers. And give us at least some bit of detail. We could really plug in, any number in the domain of this function. And if we use a calculator, we can find the square root of that number, but we're going to work with nice numbers today. So just remember the domain of this function is from 0 to infinity, including 0. And so we'll plug in a few numbers, a few x values. So our x values will be, let's see. Our x values will be 0, 1, 4, and 9. Okay, and just to show how we would plug these in, I will not really show all of the calculation for all of the examples, but for our first one here, we'd find f of 0, which is the square root of 0, which is 0. So our y coordinate, our output, we could call that y value f of x, is 0 for 0. F of 1 is the square root of 1, which in this case is 1. And one more, f of 9 is the square root of 9, which is 3. And of course, we know that this is 2. So we can plug in all of these values, or all of these points, 0, 0, 1, 1, 4, 2, and 5, 6, 7, 8, 9, 3. 9, 3 should be right there. All right, so our function looks something like that. That's a pretty good graph of it. Okay, so we're going to talk about function transformations, meaning we're going to do something to this function, some sort of operation, and we want to see, how that changes the parent function, right? Parent function is just the basic square root of x. And so we're going to start by looking at, one of the simpler cases where we look at y equals f of x plus some number k. And here we are assuming that k is a positive real number. Okay, so I'll do this in, let's see, what color will I use? I'll use green, and I'll write it in green. So we'll use, f of x, or let's say y is equal to f of x plus, and what number should we choose? Let's choose 2, right? So what is this going to do? In a sense, we can read this as we're going to take the function value, f of x, and just add 2 to it. Okay, so we can actually call this new function g of x. So g of x is just f of x plus 2. Okay, so we can do a little bit of calculation. I'm going to recycle this old table, at least pieces of it. And let me change these. So this is now g of x. And so let's go ahead and write out what the function is. G of x is equal to f of x. Well, f of x was just the square root of x, and then plus 2. So this is our new function here. We have transformed the old function into a new function using just a plus 2. And so let's plug in, let's find out what g of 9 is now. G of 9, and I'll scoot this down here maybe to kind of overlap with what we did before. G of 9 is going to be the square root of 9 plus 2, and this is now 3 plus 2. We see that we get 5, which is 2 more than what we had before. Let's do one more. G of 0, this is the square root of 0 plus 2, which is 0 plus 2, which is 2. And again, we can see 2 is just 2 more than what we had before. So if we compare to the y values from before, we're going to notice that each of these y values is just going to be 2 more than the value from before. And again, we already kind of mentioned that. That's in the way that g of x is defined. G of x is defined to be the output from f of x plus 2 more. So we're going to take the output from f of x and add 2 more, and that's going to give us 3. In general, we won't really write this. We should just kind of do it in our head. But just to show where that 3 came from. And then the output for 4 was 2 before. 2 plus 2 is, now it's going to be 4. And so I'm going to graph this in green. Let me graph these 4 points. 0, 2, 1, 3, 4, 4, and then 5, 6, 7, 8, 9. 1, 2, 3, and that is 4, 5. Okay, here is g of x. Our first function was f of x. So we could ask ourselves for this f of x plus k, if we define a new function as f of x plus k, how can we figure out what that graph is going to look like without actually having to do this little calculation here? Well, we see that the graph is just, every single point on this graph is shifted up 2 units. And so we would say, as a general rule here, now y equals f of x plus k is just f of x shifted, and we'll say up k units. Okay. And then similarly, I'm not going to do the example for f of x minus k. I think we can kind of pretty much figure out what's going to happen here. This is going to be just the original function, f of x, shifted down k units. Okay. So that was our example there. Any questions? Okay, so let's go ahead and take a look at the next one. The next one's not as simple or as easily remembered by most students. So let's go ahead and delete what we had before there. And let's see, can I make a copy of that? Maybe that would be better. Just a moment. Okay. And I'll just put that there. Okay, so now let's go ahead and go back and no. Okay. So let's try another example. Let's take a look at what we get when we use a function defined in this way. Y equals f of x plus h. Okay, so, let's copy this again and see if this helps us. So again, I'll call this new function and I'll graph it in blue now. I will call it g of x, again, but in blue. G of x is equal to f of x minus 2. Let's do that. Oh, and I have plus as my first example there, so let me use plus 2. Doesn't really matter. They're going to be very similar. And so what does this do now? What does this function look like? Well, f of x plus 2 is the function evaluated at x plus 2. So you plug in x plus 2. And so here's our new function. G of x is equal to the square root of x plus 2. And so now what kinds of numbers can we plug in? This actually changes the domain of the function because now you can plug in -2. We can find g of -2 because the square root of -2 plus 2 is the square root of 0, which is 0. So we see that now to get an output value of 0, we need to plug in -2. Notice it changed the x value there if we want to keep the same y value. And similarly, if we want an output of 1 from this function, then I'm going to need to plug in, what number do I need to plug into x plus 2 for that expression to be equal to 1? I would need to plug in -1 because the square root of -1 plus 2 is equal to the square root of 1, which is 1. What's the pattern here? Maybe if we don't see it yet, let's try another one. If we want our output value to be 2, then we need to get the square root of 4, which means that x would need to equal 2 in g. So we need to plug in 2, which is the square root of, gives us the square root of 2 plus 2. This is the square root of 4, which is 2. So I had to plug in an input of 2 to get an output of 2. And finally, let's do the last one. How do we get a 3 as an output? We need to take the square root of 9. So then x plus 2 has to be equal to 9. And that means we need to plug in 7 because 7 plus 2 is 9. So we get the square root of 9, which is 3. And so how do these numbers here compare to these? If we look at them across the board, the x values that I've chosen for g of x are all 2 less than the x values for f of x. So let's plot these points and see what that gets us. We get -2, 0. That's this point here. -1, 1. That's this point here. 2, 2. And 7, 3. And so this is what our function, our graph now looks like. Okay. So what happened there? Right? How could we describe what this transformation did? We shifted, in a sense, the graph. We slid it 2 units to the left. Okay, if you just slide that graph in black 2 units to the left, we would get our new function. So this is just essentially f of x shifted 2 units to the left. Okay. Now, it's a little bit counterintuitive, I think, sometimes for students. See, just like here in the previous problem, we had a +2, and we said that moves it up, in the y direction, +2, we think of up 2 units. But now here, this is a translation in the x direction, and the +2, whenever it's a horizontal translation, it's kind of going to be essentially the opposite of what you might expect. The +2 actually means it's going to shift to the left 2 units. Okay, so then we can generalize this and say, up here, y equals f of x plus h is just basically f of x shifted left h units, whatever number value h might be. And then what would this one be then? Can you tell me that? Y equals f of x minus h would shift which direction? That's actually going to shift to the right h units. Okay. And we could do an example of that as well if we wanted to. For the sake of time, I won't. All right, very good. All right. Okay, so we have our horizontal and vertical translations taken care of. All right, then we'll take a look at a tougher example in just a bit. But then now we have another one, another type of transformation. So let's go ahead and take a look at that one. This one is actually somewhat simple. We're looking at reflections now. Y equals negative f of x. What happens if you put a negative in front of the, you negate the entire function? Well, oops, and we're going to need our table from before. So we'll take all of this. Well, if we define a new function, and I'll draw it in green again, let's call it g of x. And we say this is just negative f of x. Well, remember that f of x is still just the square root of x. So here's g of x. It's just the opposite of the square root of x. Okay. So what is that going to do? I think this was not too hard to see. And this is actually going to have an effect on the y values of the function. And g of x is just going to be the opposite, is going to have y values with opposite sign to those of f of x. Okay, so let's plug in a couple of them and then we'll figure out what's going on. Let's start with g of 9. What is the opposite of the square root of 9? Well, this is the opposite of 3, or negative 3. What is g of 1? This is negative square root 1, negative 1. And similarly, g of 4 is equal to, ends up coming out to negative 2, and g of 0, the opposite of 0, negative square root of 0, 0 is actually not positive nor negative. So the opposite of 0 is just 0 still. Okay, so let's plot these points and see exactly how we can describe this kind of transformation. If we plot these points, they would end up at 0, 0, 1, negative 1, 2, negative, I'm sorry, 4, negative 2, and 9, negative 3. And if we graph this, we end up getting, we can see that f of x got reflected. It's like a mirror image across the x-axis, or sometimes said about the x-axis. Okay. So whenever you apply a negative to an entire function, you negate the function, you just reflect it about the x-axis. All right. There we go. And so let's go ahead. Oh, how am I going to do with that? Okay. So now let's take a look at the other case. Y equals f of negative x. So now we're applying a negative inside of the function. So, they look very similar here, but just keep in mind, one of these negatives is applied outside the function. The other one here is inside the function. And it's a negative times the function, or the negative, times the x. Okay, so let's go ahead and see what this does. Again, we will, we're actually going to notice that whenever something is applied to the inside of the function, it seems like it's going to have an effect on the x values, whereas on the outside, the one we just showed, it had an effect on the y values, right? Notice the y values changed and the x values we left the same. But now that we're going to apply, the function on the inside, I'm sorry, the negative on the inside, it's going to have an effect on the x values. Okay, so let's go ahead and define a new function. How should we define it? How about, let's call it g of x. G of x is equal to the f of negative x. And so this is going to be, remember, f of x was the square root of x. F of negative x then is the square root of the opposite of x. So g of x is equal to the square root of the opposite of x. And we think that this is going to have an effect on the x values. Let's try to get the same y values out of this function. So we need to figure out, what do we need to plug in to get these 4 output values, 0, 1, 2, and 3? Well, for 0, that's easy, because you can still just plug in 0, and the square root of the opposite of 0 is equal to the square root of 0, which is 0. But how do we get 1 as an output value? Well, we would have to take the square root of 1, but since there's a negative inside of the function, we're going to have to plug in negative 1. And if we plug in a negative 1, those two negatives will cancel, and we get what we wanted, the square root of 1, which is 1. So the number that we had to plug in was negative 1. what should we plug in to get an output value of 2? Well, we need to take the square root of 4 at some point. And since there's a negative inside of the function, we need to plug in a negative 4 so that the negative that's already there cancels out with a negative from the 4. And we get the square root of 4, which is 2. Oops. And so our output value of 2 results when we plug in a negative 4. And the last one, you might be able to see already that would come from plugging in negative 9. So notice that to keep the same y values, the x values essentially had to become their opposites. And so how is that shown in the graph? Let's take a look. And let's see if I'm going to get enough space here. I want to make sure I have enough space to graph the entire thing. Let's plot these points. And I'll do it in purple. 0, 0. I'm making them nice and big here. Negative 1, 1. Negative 4, 2. And negative 9, 3. What would you say? How was this function, how can we transform f to get g? Well, hopefully you're thinking, well, that's just a mirror image about the y-axis, right? How do we mirror something about the y-axis? Well, we have x equals 0 there at y on the y-axis. And so to make a mirror image, we just have to change the x values to their opposites. Okay, so that's what this transformation essentially does, is it will make the x values the opposite of what they were before if we want to keep the same y values. All right, so you can see the relationship there. The x values are all larger than or equal to 0, and then they become less than or equal to 0. And you can probably guess by looking at the picture that the domain of the new function of g of x is negative infinity to 0. So it just flips that domain. All right. So, maybe we could think of a quick example. Can we think of one? Well, yeah, we'll come up with one at the end once we've gone through all of the, transformations. And the third type of transformation that we'll be discussing is that of scaling, which is either stretching or compressing the function. It turns out, actually, I'm going to need this here. So let me, oops, and I forgot to fill that in. So let me do that too. Y equals f of negative x. This is going to reflect about the y-axis. All right. So let's go ahead and get our graph paper ready for our next example. All right. So let's go ahead and take a look at just one part of this. And maybe we'll start with the easier one again. So I'll switch the order of these here. Okay. So here we're assuming that A and B are numbers larger than 1. Okay. So, what numbers, what number can we choose? And so the first one here, we're going to look at what happens when you take a function and multiply it by some number. So a f of x. And so let's go ahead and give an example. And you know what? Maybe I'll do these separately here. Let's see if I can do this. Yeah, actually, I'm going to redraw that box. I don't really think we need it that big. All right. So for y equals f of x, where f of x is just the square root of x, the values that we were working with were 0, 0, 1, 1, 2, 4, and up, 4, 2, and 9, 3. Okay, so let's take a look at what would happen if we scaled this by a factor of 2. So let's define a function. I'll do it in green. Let's define a new function, call it, g of x is equal to 2f of x. And again, as we saw before, if we're multiplying the function, this 2, we can say is outside of the function because it's not inside of the parentheses f of x. It's probably going to affect the y values because g of x is just twice the value of f of x. So remember, g of x represents the output value for g, and the output is just going to be 2 times the output value of f of x. So the y value of g of x is just going to be twice the y value of f of x. So it seems like this is going to affect y values. Let's go ahead and find out. Let's plug in the same x values into g of x. We said g of x is 2 times f of x. F of x is the square root of x. So g of x is just 2 times the square root of x. So let's plug in. Let's start with g of 0. This is 2 times the square root of 0. 2 times 0 is 0. We still get 0 there. G of 1. This is 2 times the square root of 1, or 2 times 1, which is 2. G of 4, 2 times the square root of 4, which is 2 times 2, which is 4. And then g of 9, 2 times the square root of 9, 2 times 3, which is 6. So if we use the same x values, how do the output values of f of x compared to the output values of g of x. Those of g of x are just twice as large. The y values just got multiplied by 2, right? So how does that look in the picture? Well, let's do 0, 0, 1, 2, 4, 4, and then 9, 6. So what does this, what does this look like here? Is this the same as earlier when we shifted the graph up 2 units? And the answer is no, because if we look at when the graph was shifted up by 2 units, notice even the 0, 0, the point at the origin, got shifted up 2 units. And this graph no longer touches the origin. But in this case, 0, 0 stayed there, but all of the y values were multiplied by 2, right? If the y value was 2 before, it is now twice as large. If the y value was 3 before, well, now it's twice as large, it's 6. And so we would say that this was vertically scaled, and I actually had it earlier here. It was stretched vertically by a factor of 2. And in this case, we would say more generally by a factor of a, if we're sticking an a in front of the f of x where a is greater than 1. Okay, so sometimes students will ask, well, what if a is less than 1? And let's see, for the sake of time, maybe I won't show. I'll just draw the. Actually, I can maybe quickly just do it. If a is less than 1, and here we're also going to assume that a is, not only is it less than 1, but it's going to be greater than 0. Because if it ends up being less than 0, that would mean it's negative, and that would end up including a reflection about the x-axis. Okay, so we'll talk about that in a more complex example in just a little bit. But for right now, we'll restrict this next example to a number that is less than 1, a being less than 1, but also positive. And so I'll actually draw it on this exact same graph paper here. And so let's call this one h of x. H of x is equal to, I'm going to use 1/2 f of x. So we're going to multiply by a factor of 1/2. And what is this going to do? 1/2 times the square root of x. It's just going to take the output values from before and instead of multiplying them by 2, we're going to multiply them by 1/2. So we get 0, 1/2, 1, and 3/2. And again, remember, we're comparing this to the original function f of x. So how do these, and you can plug in these values yourself. You can plug in 0 for x, 1, 4, and 9, and find these output values. I encourage you to do so, but I won't do it here for the sake of time. And so notice our output values are now going to be half as large as what they were before. And so if we graph this, I'll graph it in purple, we still get 0, 0, 1, 1/2, 4, 1, and then 9, 3/2, which is 1.5. And so what did this do? It still got roughly the same shape, but you can see that it got squished. We would say that the function got vertically compressed, right? It got squished down. And we would say it got vertically scaled by a factor of 1/a, 1/2. It got compressed. Okay, and we can see that. Hopefully that shows that there. And then finally, the last example here, and maybe I'll even just kind of scoot this over right here. And let's copy this. Yeah, there's kind of a lot of information here. So this is the last part of it, but this is very important. Maybe I should have said that at the beginning, that we know how to, or how these different values affect the graph of the function. Okay, so my battery is also dying, so I'll try to hurry. So let's go ahead and take a look at what the X and Y values were originally. Okay. And so now we're going to take a look at a function. Let's call it, let's see, what color can we use? I'll use a light blue. We'll call it g of x, which is f of 2x. I'm going to use the same factor 2 again, but notice that the 2 is now inside of the function rather than outside, right? Last time it was outside, and now it's inside the function. So we said before that this is probably going to have some sort of effect on the x values. And so let's write out the function. This is f of x was the square root of x, so now it's f of 2x, so it's the square root of 2x. And so I'll write the function g of x is just the square root of twice the x value. Now, how is this going to affect the x value? Well, say that we want the same output values, 0, 1, 2, and 3. Notice that 2 there is going to double what we have inside of the square root. It's going to double whatever we plug in. And so it seems like here we're going to want to plug in numbers that are half the size of what they were before, so that when they get doubled, we get a number that we can easily take the square root of. So let's try plugging in. Let's say we'll start with g of 0, because that one's nice and easy. This is the square root of 2 times 0, which 0 is a nice number. It has a lot of nice properties. So this is the square root of 0, which is 0. Okay, so if we plug in 0 as our input, we still get the same output. That's nice. But now let's plug in, hey, let's plug in 1/2 into this square root function. And 1/2, oh no, that's a fraction. But it turns out that it's going to work out nicely, because when we double 1/2, we get 1 in that square root, which gives us an output value of 1. So 1/2 is actually a good input for this function. What else can we plug in? Well, how about 4/2 or 2, right? This 4, I'm going to divide it by 2. That gives us 2. I'm plugging that in. And so when I plug in 2 into 2x, I get 2 times 2, which is the square root of 4, which is 2. So an input of 2 gives me an output of 2. And then the last number I'm going to plug in is 9/2. If I plug in 9/2, I'm going to double that and get a 9 in the square root. The square root of 9 is 3. And so I get 3 as my output for an input of 9/2. And so notice that by plugging in this 2 inside of the function, what it essentially has done here is it has made these x values half of what they originally were. So what does that mean? Let's go ahead and take a look at the graph. We'll plot it in that blue color. 0, 0 still on there. 1/2, 1 is there. 2, 2. and 9/2, which is 4.5, 3. So what did this do here? How would we describe that? I'm going to draw arrows here, but the x values, as we saw from the table, the x values were all cut in half. And so this function is being squeezed or compressed horizontally by a factor of it's being scaled by a factor of 1/2 for our problem. I'm going to put 1 over b here more generally if we plug in b into the function. Okay. So similar to the previous case, if we were to plug in a fraction, so if we were to look at, let's use a different color here, f of 1 over 2x, which is equal to the square root of 1/2 x, we can probably see that in order to take the square root of the number that we plug in, it's going to have to be twice as large as a perfect square. So for example, if we call this g of x, if g of x is equal to the square root of 1/2 x, then g of 18, which is 2 times 9, when we plug in 18, it's twice a perfect square, so that when we multiply the number 18 by 1/2, it reduces to half its size, which is a perfect square now, and we get an output value of 3. So for the output, for the output value of 3, the input that we actually need to plug in is 18. That is twice 9. And this is going to work similarly here for the rest of these points. And so what we're going to get is a graph that looks like this: 0, 0, 2, 1, 8, where's 8? 8, 2, and then 18, 8, 9, 10, 11, 12.